Welcome back, guys. Today we are going to be covering section 1.6. Final section we'll be looking at from chapter 1. And it has to do with some of the things we've talked about the last couple of lessons. So compound and absolute value inequalities. 1.4 was all about absolute value. 1.5 was about inequalities. And so today we're going to be kind of combining the two. And the first compound inequality we're going to look at, let me get my highlighter out, is something that looks like this. So how would I read this? What I just highlighted in yellow. It says negative 13 is less than negative 2x plus 7 is less than or equal to 10. So I read it there kind of as a three-part inequality. Negative 13 is less than negative 2x plus 7 is less than or equal to 10. But it's also pretty common to throw this word and in and kind of repeat the middle part. What this triple inequality says is that negative 13 needs to be less than negative 2x plus 7 and negative 2x plus 7 needs to be less than or equal to 10. And any solution that we find has to satisfy both of those inequalities, those separate ones. So how do we solve this? Well, what I'm going to do is I'm going to write the original inequality down. So negative 13 is less than negative 2x plus 7 is less than or equal to 10. And normally in a problem like this, we would ask ourselves, okay, maybe I should subtract 7 on both sides or divide by negative 2 on both sides. Well, instead of both sides, all we're going to do is swap out the both for all. On all three sides, on all three parts of this inequality, we can do our mathematical operations as long as we do them to every single part of the inequality. So, for example, I want to get x alone, so maybe I subtract 7. And I need to subtract 7 on all three parts here. So negative 13 minus 7 is negative 20 is less than negative 2x is less than or equal to 10 minus 7, which is 3. Great, so here we are. I now need to divide by negative 2 to get x alone. So I'm going to do that, but I'm going to do that in all three parts of this inequality. And remember, inequalities, when we're multiplying or dividing by a negative number, the sign does have to flip, right? And so what will we get? We will get positive 10 is greater than x, which is greater than or equal to negative 3 halves. And just because how we are used to seeing it is kind of the other way, the lesser value on the left, I'm going to flip this. I'm just going to say, okay, so negative 3 halves is less than or equal to x is less than 10. Both of these two lines say the exact same thing. It's just the bottom one is how we're more used to seeing it. So what does this mean? This means I can plot this on a number line. Anything between negative 3 halves, which is negative 1.5. I'm going to use a closed dot there because it was less than or equal to. Anything between that and 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I'm going to use an open dot there because it was just less than. Anything greater than or equal to my leftmost limit and less than or equal to my rightmost limit should satisfy both of these inequalities. So looking at this, something kind of important to note that I'm going to keep referring back to. An and inequality will typically look something like this, where there's a beginning point and an end point. Maybe the dots are open, maybe the dots are closed, but there's a region in between that is shaded in between two dots. And that's going to be important. We're going to see that again and again and again. So a couple of things we could do, always a good idea to test, make sure that some values in there work. So what am I going to do? I'm going to grab my calculator. And the calculator, I'm going to use some of the functionality of my graphing calculator to do this quickly and efficiently. So first thing I'm going to do, I'm going to pick a value that should not work over on this side of my number line. Something that's not shaded And it's always best to try to pick something really close to your limit, really close to that dot. So since -3/2 is -1.5, I might try plugging in -2. I'm going to say -2 store in X. That's telling the calculator whenever I press X, I want it to use -2 as the value. So then I'm going to type in the middle part of my original inequality, -2x plus 7. And it knows to use -2 as the X value. So it's going to plug it in there, and let's see what we get. We get 11. Now let's look and think back to our original inequality, see if this is true. Is, change colors to green, is 11 what we got greater than -13? Absolutely, 11 is definitely greater than -13. So that checks out, but what about the other one? Because both of these have to be true. Is 11 less than or equal to 10? Answer's no there. And so we definitely know that -2 does not work. I'm going to put a little X there just to remind myself I did check that. What about a value that should work? Again, choose one that's kind of close to one of your limits. We could choose 0. That's pretty close to the limit. So why not? 0 is an easy one to plug in. 0 store in X, and then I'm going to hit second enter to go back to 2 entries in my calculator. And I get 7. Let's check 7. Does 7 satisfy both of these criteria? It is greater than -13, and it is less than or equal to 10. And so plugging in 0 got me 7, which does satisfy those criteria. Lastly, let's try something on the other side that should not work. And I think I'm going to go for just 10, because remember, open dot on 10 means it is not in the solution set. 10 store X, second enter. We get -13. Let's check if that satisfies the inequality, both parts. -13 is, well, it's actually not greater than -13. We needed something that would be greater than -13. It wasn't. And since it has to satisfy both parts, we know that doesn't work. So always a great idea to check your answer, plug in some values close to your limit. Looks good from here though, feeling reasonably confident that this number line is correct and that this, I'm just going to box that bottom one, is the correct algebraic solution. -3/2 is less than or equal to X is less than 10. So for and inequalities, the big thing to remember is that whatever solution we get has to satisfy both parts of the inequality. Contrast that to an or inequality. An or inequality, as shown on the screen right here, it's like the word or in the English language. Solutions can satisfy one of those inequalities or the other one, or both. And if it satisfies at least one, we're good to go. So how are we going to do this? Well, we were told that X plus 3 had to be greater than 4, or X plus 1 had to be less than -3. And the good news with this is we can just solve these independently. I'm going to subtract 3 on both sides on my red. So that means that X has to be greater than 1, or I'm going to subtract 1 on both sides on my blue. So X has to be less than -4. X needs to be greater than 1, or X is less than -4. So what does that look like on my number line? X needs to be greater than 1. So open dot and kind of shading that away. Or X is less than -4. So -4, open dot, and shading to the left in the less than direction. Any X values that when we plug them in to my original compound inequality satisfies at least one of those two parts, good to go. So let's try some things that shouldn't work and should work. I think I'm going to try -4, and I'm going to just demo how to do this by hand. If I plug in -4, -4 plus 3, is that greater than 4? So that'd be -1, is that greater than 4? And no, -1 is not greater than 4. But remember, we only have to satisfy one of the two parts of this compound inequality. So I'm going to try it on the second part now. Plugging in -4 to the second part is -4 plus 1. Is it less than -3? And subtract 1. So is -4, I'll put my question mark there, less than -4? It is not. So I tried plugging in -4. It didn't work for either of those. So it's not in my solution set, which is good because it was an open dot. We don't want to include it in the solution set. Let's try plugging in 0. I love plugging in 0, and it's even better if it's kind of close to my limit. So I'll try plugging in 0. 0 is, let's see, 0 plus 3. I'll plug into the red one. Is it greater than 4? And we can see that 3 is not greater than 4, so that doesn't work. What about 0 plus 1? Is it less than -3? And 0 plus 1 is just 1. 1 is not less than -3. That does not work. And I'm sorry, put my x right over 0. So we tried plugging in -4. We tried plugging in 0. Neither one worked. Maybe let's try something that should work in the red shaded region. So 1 was an open dot, but we could try 2. We could try plugging in 2. So I'm going to plug it into the first one. 2 plus 3. Is it greater than 4? 5. Greater than 4? Yes, it is. And the great news with an OR is we can actually stop here because we only need it to satisfy one of those two parts of the compound inequality. Since plugging in 2 satisfied this first one that I just circled, it is a valid solution. So checked a few different spots in my number line, feeling really good. Final answer, x is greater than 1 or x is less than -4. Now, before I move on from this screen, I want to point something out. I mentioned in the previous example that and inequalities usually look something like this. Again, maybe open dots, maybe closed dots. But the bottom line is it's the area shaded in between the two dots. Look at the graph right now for our OR. This graph is going off and pointing in different directions. This is a very common thing you will see. I'm not going to say 100% of the time, but ands typically point in and we shade the region between the dots. Ors point out towards opposite ends of the graph. All right, something to keep in the back of your mind because it will start to play into some of these inequalities as we get into absolute value. So right here, we've got absolute value inequalities. The absolute value of x is less than or equal to 2. And before we even try to do anything with this, what I recommend is let's think about what absolute value means. We learned in section 1.4, absolute value is the distance of whatever's inside it, in this case, distance of x from 0, always distance from 0. So see if this makes sense, what I write here. I think we can translate this to distance of whatever's inside the absolute value. So distance of x from 0 is less than or equal to, because that was the sign, 2 units. Think about that. The absolute value is the distance from 0 of whatever's inside it. So what this is saying is that the distance of x from 0 is less than or equal to 2 units. In my mind, that means we can go 2 units this way, we can go 2 units that way, and everything that's shaded should be within 2 units of 0. That absolute value, that distance, it's within 2 units of 0. That distance is less than or equal to 2. So I put a little prompt there on the screen. Can we write this as an and inequality? Do you recognize it? We got 2 dots, we shaded what's in between it, between the 2 dots. So if we think of it and see that number line down there, we could write this as -2 is less than or equal to x, is less than or equal to 2, saying x needs to be sandwiched in between -2 and 2. Okay, so anytime we see an absolute value inequality where the absolute value is less than, that means that it is going to be an and inequality. And a couple ways to think about this. Anytime we see absolute value and we have absolute value is less than, it's going to become less than, if you will. Or my personal favorite, because this here looks like a sandwich with x in the middle of -2 and 2. Anytime we see a less than, absolute value is less than inequality, we have a and which, so that less than corresponds to an and. Just a couple silly things to help you remember. When you see absolute value as less than, it can be written as an and inequality, and we will typically be shading in between our dots. Contrast that to, you know what's coming. What if we see an absolute value is greater than? Or maybe I should say absolute value is greater than. And no, I didn't accidentally misspell greater, but if we see absolute value is greater than, if that's the symbol here, we can turn this into an or inequality. So again, thinking about that definition of absolute value, distance from 0. This is saying, and I'm just going to abbreviate a little bit, distance of x from 0 is greater than 5. Again, just abbreviating for time's sake, but the distance is greater than 5. We have to be more than 5 units away from 0. So 2, 3, 4, 5. In your mind's eye, I'm hoping you can see, okay, that's saying we can only shade things that are greater than 5 units away from 0, further away than 5 units. And so there is our or inequality where we're, again, pointing outwards. And if we have the number line, we can also kind of translate that to, okay, so this would be x is less than -5. I should label these. Or x is greater than +5. Anything in those two ranges will, in fact, be further away than 5 units from 0. It will have an absolute value greater than 5. So these previous two examples, this one and the one before it, are just to build the understanding of absolute value inequalities. What are they really saying? They're saying distance from 0 greater than 5. So we have to be further away than 5 on either side. Or distance from 0 is less than 2, less than or equal to. So we need to be within 2 units on each side. Now, what makes these two examples kind of elementary, if you will, is that the only thing inside the absolute value was x. What if we have a more complicated expression in there? So that's what I'm going to kind of demo for this last part of the lesson. We're going to see some examples of how this all works when we have absolute value of 2x minus 4 is greater than 8. So definitely more complicated than just the x we saw. But that's okay. Because if you look at this, first thing I hope you notice is, okay, absolute value, we have a greater than sign. So that means this is going to be some sort of an or inequality. And let's look at this example. When the absolute value of x was greater than 5, it meant that, okay, we need to be more than 5 units away from 0. So whatever was inside those parentheses, or those absolute value, I should say, x had to be less than -5 or greater than 5. So right here, what we are saying is that we need to do something because the distance is greater than 8. We need to do something with -8 and +8, saying let's only shade things that are further away from 0 than those two numbers. And if we think of that, if we can see this really quick number line, either on paper or in our mind's eye, we can start writing this OR inequality and solving it. I'm going to say, okay, so looking at this part that I just highlighted on the number line, whatever was inside my absolute value, 2x minus 4 has to be less than -8, or let's look at this part. Whatever was inside the absolute value, 2x minus 4 needs to be greater than +8. And that's why that number line is so crucial, just to kind of see in your mind's eye. If you can see that the absolute value is greater than something, that means we're pointing outside because we got to be far away from 0. That'll help you a ton on these problems. So now we can just solve these normally. 2x, add 4 on both sides is less than -4. X is less than -2. Or add 4 on both sides. 2x is greater than 12. So, and I should have written that a little bit above. 2x is greater than 12. So x is greater than 6. It looks like my answer is x is less than -2 or x is greater than 6. So I'm going to put that on my number line. -2, 2, 3, 4, 5, 6. Greater than, so open dot and shade. Less than, so open dot and shade. And let's just test a couple points. One that shouldn't work. Well, we have two areas that should work actually. So let's test one that should work in this region. So I might try -3. I might just plug it in. Absolute value of 2 times -3 minus 4. Is it greater than 8? Plug it in by hand. So that would be absolute value of -6 minus 4, which is the absolute value of -10, which is 10. Is 10 greater than 8? Yes, it is. So -3 did in fact work. This is looking good. 0 is not shaded. I love plugging in 0. So I'm going to say absolute value of 2 times 0 minus 4. Is it greater than 8? Well, 2 times 0 is just 0. So 0 minus 4, absolute value. Is it greater than 8? So -4. So is 4 greater than 8? No, it's not. So we know 0 didn't work. We didn't want it to. And something that should work on the other side, maybe 7. Absolute value of 2 times 7 minus 4. Is it greater than 8? And I wrote a parenthesis when I should have done the absolute value symbol, so I'll fix that. 14 minus 4. So that's absolute value of 10. So that's 10. Is 10 greater than 8? Yes, it is. 7 worked, matches our number line. Feeling really good about this answer and this number line now, after just checking a couple answers to make sure we didn't make a silly mistake. So that's one example of an absolute value inequality. We got one more, and let's just give it a go. Absolute value of 3x minus 12 is less than or equal to 6. I hope the first thing that you notice is, okay, it's an absolute value inequality. It's less and less than. So that means that on my number line, I need to be less than or equal to 6 units away from 0. So that means I'm somewhere in here on my starting number line. And that means it's an and inequality. So let's go ahead and set that up. Based on this number line that I just drew, -6 is my lower limit. Needs to be less than or equal to 3x minus 12, which needs to be less than or equal to my upper limit from my number line, which is +6. Again, thinking in absolute value terms, whatever was inside the absolute value has to be within 6 units of 0. Distance has to be less than or equal to 6. So that means it's between -6 and 6. I'm going to add 12 everywhere. Notice I said everywhere, not both sides, because there are 3 sides in this case. So 6 is less than or equal to 3x is less than or equal to 18. Divide by 3 everywhere, and we will get 2 is less than or equal to x is less than or equal to 6. 2, 3, 4, 5, 6. 2 is less than or equal to x is less than or equal to 6. I will shade in between. And then I'll just check a few points. And maybe I'll do some mental math for this one. Try 0, plugging in 0. 3 times 0 minus 12, so 0 minus 12. That's negative 12. Absolute value of negative 12 is just 12. That is not less than or equal to 6. So that did not work. That's okay, didn't want it to. Maybe I'll try 5, because 5 is kind of close to the edge. 3 times 5 is 15, minus 12 is 3. So we need absolute value of 3, which is 3. 3 is indeed less than or equal to 6, so 5 worked. We wanted it to. And how about 7? 7 shouldn't work. Let's just check it. 3 times 7 is 21. Minus 12 is 9. Absolute value of 9 is 9, which is not less than or equal to 6. 7 did not work. So it didn't take that long. That's one of the things I'm trying to demonstrate. Checking doesn't have to take a super long time, but it can just give us three quick checks and saying, okay, it didn't work where I didn't think it should. It did where I did think it should. I'm feeling even more confident about my answer now. So that is 1.6. I know it was kind of a lot. We started here introducing and or inequalities, those compound inequalities that have multiple parts. And then we started, really looking at the logic and the conceptual understanding behind absolute value inequalities, that the distance of whatever's inside the absolute value has to be, in this case, less than or equal to 2 or greater than 5. And so we can use that to figure out, is it an and, is it an or, and set up our starting inequality, our starting number line. And then we put it all together, absolute value with changing those complicated absolute values into compound inequalities, ands and ors, and then checking at the end. So not an easy section. There's kind of a lot here. It will take some practice, but I'm hoping this video did make some sense. Gives you at least some reinforcement for what we talked about in class. If you have questions, as always, please let me know. I would love to hear from you and be able to help you with your understanding of this topic. But that is all for this video, and we will be in chapter 2 in the next one.